Now, as we have discussed a few numbers, the idea is that I will try to provide you an overview about the transition from the zero energy buildings into more efficient, if you can call it like this, smart cities. And this is something which will be dealt in 5 sections in the presentation. So a bit about the introductory, a bit about the energy efficiency, zero energy buildings, the cities, and some thoughts. Allow me to begin with a short story from the past, especially for those friends who are not necessarily from Europe, or for some of our students. Back then in the 80s, early 80s, if you were in favor of renewables and against nuclear power, you were almost considered to be suspicious. You could be an agent of Moscow, it was communists in those days. You could be an anarchist or something like that, because the official policy was we need nukes, period. Then Chernobyl happened in 1986, and renewables all of a sudden became a bit more popular. Towards the 90s, I had the good luck of doing my Masters of Science in Cranfield in the UK. The policy was still, well, not so much nuclear, but at least it had to be coal. So I did my Masters of Science course on energy conservation, and my thesis was an expert system on renewable energies. And I get an examiner who was a senior guy for British Coal, which is obviously not exactly the ideal constellation. So he said, it was very nice what you did, but dear fellow, we do need some big power plants with coal or gas to survive. This piece of news played in the media a few days ago. Britain, for the first time since Queen Victoria ruled, spent a whole week without any coal-fired power plants running. And this was last week. I'm sure that the guy from British Coal is in retirement for decades now, but I think it's interesting thinking of how times are changing. So it is within this line of approach that the European energy policy has been considered. And this is a policy that, as I'm sure most of you know, or all of you know, is mainly based on the 4 goals of reducing greenhouse gas emissions, increasing the share of renewables, improving energy efficiency, and improving interconnection, because otherwise the first 3 goals make little sense. This has to be done in order to achieve the 2030 goals, but this also has to be done because the European Union certainly knows that energy efficiency, the environment, and economic growth go hand in hand. Energy efficiency makes jobs. Energy efficiency is not only good for the environment, but it is supporting the security of energy supply. Energy efficiency provides competitive advantages to the businesses who apply it. And this is one of the main reasons why we're doing nice conferences like this, and why we have cooperations with industry, and why we try to promote our work. And if we speak about efficiency, clearly the building sector is a crucial one, because these are known statistics. I think if you look at the European Union of the 29 members, I'm not sure whether Britain will be with us next week or so, but who knows? Buildings account, roughly speaking, for 40% of the energy demand. Approximately a quarter goes to households, residential buildings, approximately a quarter goes to services. So if we want to achieve the goals set for 2030, it has to be done by buildings. Now, energy consumption in residential buildings, and let's stick for a moment to residential buildings, varies. And if you see the consumption by end use per dwelling, as it was a couple of years ago, you can see that you can have anything between half a ton of oil equivalent per dwelling and 2.5, roughly speaking 5,500 kilowatt hours per square meter, and 5,500 kilowatt hours and 30,000 kilowatt hours. And you can see also distribution. Heating is even in the space heating is even in the warm European South the main cause of energy consumption. But of course, this figure is not specific energy consumption, but energy consumption in absolute terms. So if you have a look at the small picture on the upper left corner of the building, you can see, for example, that the typical apartment, let's say in Central or Eastern Europe, gives every tenant 20 square meters. So if you are in Romania or in Greece, you get per capita something close to 18 or 20 square meters to live, whilst if you are in Germany or in Luxembourg, you get almost 45. So it is important to understand that if we speak about energy efficiency in the building sector, we have to use specific consumption values. But if we speak of our goals and energy efficiency overall, then this has to be dealt with in absolute terms. Because, and this is one of the bad news of the day, energy efficiency in the building sector has clearly improved. As you can see, from 1990 to 2016, we have achieved an increase in efficiency of almost 25%. But energy consumption as a whole has increased because, and this is the red line on the top of the slide, here, because we have more dwellings and more space per capita. The same applies for cooling. This is the specific cooling consumption, and this is the total cooling consumption. So the good part of the story is that on average we live in much better conditions than we used to 20 years ago. The baddest part of the story is that because we do this, we consume on total a lot of energy and a lot more of energy. This is a very nice slide because it shows what the drivers are that influence energy consumption. So you can see energy consumption decreases, a specific one because we have better buildings, but we have more appliances. How many televisions do you have in a typical 4-family member household? We have larger homes. We have an efficiency progress. We have much more efficient equipment. And we have a better behavior. We're aware and conscious of the environment. But overall, the tendency is rising. If I may show the curves, let's say for Greek situations, within 40 years or so, we reduced energy consumption by an order of magnitude, or perhaps by a factor of 7 to be more realistic. So from something like 300 kilowatt hours per square meter to something, let's say, about 50 or 70. And this is a quite important evolution. But given the fact that the number and the consistency of the building stock does not change fast, as a matter of fact, due to the recession for the last 10 years, it almost doesn't change at all. We have to live with a building stock that is aging, that is inefficient. By the way, this is a European problem. So whatever progress is made has to be dealt with on 2 levels. A, improving the existing buildings. B, making new buildings that are much more efficient. And this cannot be done, I dare to say, on a single building level. I think this is also very well mirrored in the evolution of the regulatory framework in Europe. So we went from the initial energy performance of building directive, which foresaw the necessity of energy studies and energy certification, to the previous version, which was valid until last year, which foresaw the introduction of nearly zero energy buildings, cost optimalities, and smart metering. But as even Europe realized, even the guys sitting in the European Parliament realized that this is not enough, we have the latest version of the EPBD, which says that the building stock has to become a nearly zero energy one by 2050. And for those young guys or students sitting there in the back, 2050 will be the time when you are at the height of your careers. I will be most probably, if I'm lucky, in pension then. We have to integrate ICT, automation controls. Buildings have to be able to support electric vehicles because there is no sense in talking about zero emission mobility if our buildings are not able to support and charge our electric vehicles, otherwise we can forget it. And we have also to face energy poverty. Okay, let's stick to the middle part of the column, nearly zero energy buildings. It's nice to put together a piece of legislation that says you must do zero energy buildings. Here's what a nearly zero energy building in various parts of Europe looks like. If you're in Austria and build a house, it has to have a maximum consumption of 160 kilowatt hours per square meter. If you do the same exercise in the region of Brussels, it has to come up with 45 kilowatt per square meter. In Cyprus, 100. Denmark, 30. Danish people have probably the tightest regulation overall. The Germans, who like to pinpoint everyone else for not sticking to the rules, played this very nasty trick, although the EPBD explicitly says that you have to have a strict numerical limit for nearly zero energy buildings. The Germans don't give a damn. They say, okay, it's 40% of the reference building. And similarly, you can see non-residential buildings. What's also important is that despite the call for a uniform methodology, you don't have in all the countries the same energy consumption causes being considered. In a sense, it makes sense, but it's still quite peculiar. So, if we think of the strategy in the energy chain with respect to efficiency, it's clearly accepted, and every student who has a decent degree in HVAC or energy design of buildings should know that we have to minimize the demand and introduce renewables so that we go towards the zero energy approach. But it's not necessarily a straightforward task if we have to start from the equipment level. Let's have a very efficient chiller, move to the building, let's have a zero energy building, and move over to the city, or we can move a bit more freely and arbitrary between those goals. In any case, the strategy, I think, is pretty much known. You will listen after the break to my dear colleague and friend, Professor Ravadinos, speaking about reducing the demand, let's say, by means of green roofs, if I remember correctly. We heard a bit about ventilation, HVAC systems. Our dear colleague from Cairo showed us a few slides about passive solar systems. So you have to put this all together, and hopefully it works. It's clearly also that within Europe you cannot have a straitjacket. Not all the cities, not all the regions have the same climate. These are the U-value requirements for, let's say, 8 European cities, from Nicosia to Stockholm. And you see that you go from 0.86 to Malta to 0.18 to Stockholm. It's a huge deviation. However, if you normalize it based on the heating degree days, then it makes much more sense. So there is a sort of sense behind it. And we can also, and this goes way beyond the scope of today's presentation, but we have to be flexible, and yet we have to be decisive, because we have to choose heating systems and cooling systems and hot water preparation systems, and you can choose anything you like. Nowadays, you can see some nice stands outside in the break, I think. You can have highly efficient air-to-air, or air-to-water, or water-to-water heat pumps. And if you make the wise, correct the selection, having the appropriate heat pump for the appropriate heat distribution system, then you can have a very nice efficiency overall. And you can link it also with your hot water production, or you can use a solar thermal system for the hot water production, or you can use an absorption chiller linked to the solar thermal system. You name it, we have it. It has to be compatible. Do not try to use a low temperature system like a solar thermal system with baseboard heaters. It's a man-made disaster. It has to be efficient. It makes a huge difference if you have a water-to-water heat pump than compared to an air-to-water heat pump. Is it suitable for your climate? It has to comply with national regulations, which is something which we tend to forget. It's not the same regulation that governs the heating selection or sizing system in Germany and in Greece. There are differences. And of course it has to make economic sense, because otherwise no one will pay it. This is what a nearly zero energy building looked like 12 years ago when it was decided. I like this example. It's a result of a cooperation, let's say a sort of an all-star team, Demokritos, the National Research Center, our department and the laboratory which I have the honor to chair, the School of Mechanical Engineering and the Technical University of Athens, and Sol Energy. You take an office building in the heart of the city, you equip it with flat plate collectors, Fresnel concentrating collectors, a geothermal heat exchanger, an absorption chiller, photovoltaics, you name it, we have it. for the year 2005, when it was designed, it was really state of the art in an otherwise conventional building. No passive systems, nothing else, because the plot and the building were there. And you come up with an energy consumption, it's an office building, mind you, below 60 kilowatt hours per square meter, it would be a zero energy building, nearly zero energy building with today's standards, and the solar fraction of something close to 70%. Of course, this was designed from the beginning. It's a much different story if you have to go and work with a building stock. And to have an idea about the goal that lies ahead, if we want to comply with the goals we have agreed to reach by 2030, we should renovate in the next 8 years or 9 years approximately 600 to 700,000 residences. Deep renovation, thermal insulation, windows replacement, new HVAC system, waste heat recovery, renewables. And this is, in my humble opinion, where we have to switch from the building to the city level. Because if you want to do a zero energy building, whatever, there are 4 parameters that present limits. To begin with, the technical applicability. In the urban environment, you have limitations. You don't have southern orientation, which would be ideal for a passive system. You cannot use always natural ventilation or nighttime cooling because it's too noisy or it's too dirty or whatever. There is no security. Then you have the problem with renewables, which is a possible differentiation between the supply and demand chain. If you're in an office building, it's nice. Your photovoltaics will work in the daytime, your computers will be running, lighting will be running, that's fine. If it's a residence, it's not so fine. Storage is clearly an option. It was one of the, I think in the first presentation in the morning, the development in batteries will play a crucial role in the way in which we understand zero energy buildings. But it's still not a straightforward way to go. And of course you have operational restrictions and economics. If you are running a big hotel like this, or it's not a big one, but it's a good one, let's put it like this, then you have requirements from the sales department where you have to provide hot water recirculating 24 hours a day. This is not energy efficient, believe me, but it's not up to debate. So putting all those things together, we move from the previous research project that went into practice, that was the zero energy building in Athens, to another project, which is the Zero Plus Positive Energy Settlements project. 4 settlements in 4 countries, Cyprus, France, Italy, the UK, where the idea is to put a settlement that has a zero energy balance. Because on a settlements level, I can offset the negative orientation of one building with a positive of another. And if I don't have space in the basement for a 6,000 liter storage tank to utilize my thermal solar system, I can use the neighbors. And if I introduce a grid, a smart grid, that links central power generation and links the buildings with each other and links the charging stations for my electric vehicles and links everything else, then things start becoming really interesting. Because what I would ideally like to do is to be able to have buildings connected to each other. Not to utilize, not to have to go all the way up to the transmission system operator, the TSO, with my photovoltaic production, so that he can dispatch again the load to the consumer who might be next door. That doesn't make sense. So if I'm able to set up a grid, it can be a microgrid, five buildings. It can be a bigger grid, 500 buildings, I don't really care. But if I can set up a grid that allows us to switch to self-producing energy networks, where you have the communication between buildings, and this self-producing energy network is integrated in the main grid. It can also be independent. If you are in an island far off the mainland of Greece, it can be an independent one. If you are in a neighborhood of Thessaloniki or Athens, it doesn't have to be. It can be fully integrated. And so you can start purchasing or selling electricity to your neighbor without, for example, having to pay the fees that the TSO, the transmission system operator, has to collect. It will make an entire different approach for the feasibility of renewables and storage. And this will also enable a much better integration of small-scale renewables. We can have 3 technologies that can be fully utilized in this way. You can have micro CHP, let's say a 1, 2, 3 kilowatt CHP system, combined heat and power generation, where you can produce heat for your heating system, give the electricity to your microgrid, and run throughout the year a very efficient, both in terms of energy and costs, power generation system. You can have small-scale electricity generation, as we know it, photovoltaics. Building applied, building integrated, I don't care, it's the same from the energy production aspect. Hybrid PV and solar thermal systems, which are a very nice option if you don't have enough space on the roof, and space on the roof is always a commodity of short supplies in the cities. You have satellite dishes, you have chimneys, you have staircase wells, you have any sort of water tanks, anything. Or you can also have, if you are in a windy exposed area, micro wind generators, 5, 10, 3, 2 kilowatt systems, small ones, fairly quiet, not the most efficient way to generate electricity, I have to admit, but you can decentralize it. Or, if the climate and the morphology allows, you can have also an integrated thermal generation from renewables. A district heating or a district cooling grid that utilizes biomass. It can be urban waste, domestic waste, or it can be the leftovers from agriculture. You can utilize geothermal energy. You can utilize a solar thermal system. The Danish have been pioneering in that in the 80s, late 80s, early 90s. Okay, it's not easy to apply this technology, for example, in Greece, let alone in Cairo for heating, because we have such a short or almost non-existent heating period that it wouldn't make sense. But it makes a lot of sense, and it's been done for the last 20 years now in Paris, where they heat up, they cool down the whole defense office area with geothermal energy from the sand. So we have to think in this way. And just to give you an idea, why this is important, this is from an ongoing project we have. Take, for example, 60 residences. This will be a neighborhood. It can be 3 apartment blocks or 60 single family houses, I don't really care. And try to see how you can utilize, by means of a smart grid and some sort of smart appliances, the different operational schedules. So everything that is blue, if I can see correctly, which is very difficult without my spectacles, is when you use a microgrid. Everything that is yellow is when you purchase grid electricity from the main grid, or the other way around, it doesn't really matter. And here you have for every apartment for the 24 hours how it works. If you can exchange electricity between the members of the microgrid, then you can reduce by 42% the electricity purchased from the grid. Remember, we don't have feed-in tariffs anymore. We live with virtual net metering or with net metering. So it makes a huge difference if you exchange electricity instead if you use the metering option. This difference in terms of operational costs would mean that the typical residents would pay, let's say, 620 euros a year for heating and cooling. If it has only the microgrid, load management, you have savings of 10%. If you utilize some micro CHP, savings go down to 20%. And if you have polygeneration with renewables, your savings go up to 27%. Now, these are annual operational costs. I haven't spoken about the initial cost and the investment, which is another sad story, which has still to be reduced, but it gives you an idea of how we should work. So I think there is a long and winding road, to remember a nice song by the Beatles, that leads us to zero energy buildings on a large scale. It starts with a political decision, which is there. It has a lot to do with codes and standards. It has a bit to do with ASHRAE, for example, in that sense. Information, certification. You have to get owners, users, and managers engaged. The public sector has to lead by example. It's not always easy. Incentives and finance have to be correct. Not necessarily spending money, throwing money out of the window, but making things a bit more easier for the investor. Getting the companies, the providers of technical solutions involved. Utilities have to play part of it, and then you can come up with zero energy buildings. Obviously, energy efficiency is not a goal by itself. I think we have heard about this quite a nice couple of presentations in the morning. You have, for example, thermal comfort, lighting, indoor air quality. You have function and aesthetics, otherwise you would build a bunker. No reason to talk about. And you have cost effectiveness. You have air pollution problems. If you remember a couple of winters ago, when the oil price increased by 50% due to taxation, we had a record PM10 concentration of 220 milligrams in Thessaloniki and about 195 in Athens. The limit is 50. So if you start burning your old furniture, this is what happens. We have a problem that is called fuel poverty, and it's becoming steadily quite visible because for years it was not so much. So you have 4 countries in Europe where more than 30% of the people are not able to heat their homes adequately. You have 3 rich countries where the problem is not existing. You have 3 countries where more than 28% have significant arrears on their utility bills. And you have countries, again, 3 countries where people live in dwellings with permanent leaking problems, mold, damp walls, and so on and so forth. If you think this is only Eurostat, these are some results we published last year with a colleague of mine who did a big field study in northern Greece. One of the questions, one of the about 60 questions we filled out with interviews was, below what internal temperature did you switch on the heating last winter? Half of them switched it on, below 16 degrees. If you live in Western Macedonia, in Kozani, in Florida, in Kastoria, for the colleagues not from Greece, the design temperatures there are -10. So that doesn't make a lot of sense. And you had approximately 30% of the people who heated their houses for less than 5 years. This is fuel poverty. And this cannot be addressed with fuel supplements. We have to make our buildings more efficient. Of course, this cannot be done in a miraculous way. We have to bridge the gap between what is cost optimal for a conventional state-of-the-art building and what is cost optimal for a zero energy building. Otherwise, the market will not move in that direction. So we need smarter designs. We need a better integration of the buildings in the grid. We need better insulation materials, HVAC equipment, whatever. Is there a market for this? There's a huge one. These are the figures from one of the nicest studies that one can find about the impact of the directive on nearly zero energy buildings in Europe. And it gives a rather modest assessment that in the decade 2020-2030, the thermal insulation market will double or treble. Waste heat recovery systems will be needed 10 times more than today. Energy efficient glazings will be needed 10 times more than today. Heat pumps will treble with a bit of luck. The same applies to biomass-fired boilers, and the same applies to solar thermal systems. In other words, this is a nice outlook for young engineers. And this is a nice outlook for a market that has not experienced golden days in the last few years. Therefore, and I think it's time to conclude, we have the goal, we have the means to go there. In theory, we have also the will. What is needed is to put all those things together, the ingredients together, in the right mix, and give the push that is needed to the market so that it moves in that direction. You don't need a crystal ball to see the future. It was on a billboard back in '73 in Oregon State. And this is what energy conserving people should be called smart. Thank you very much indeed.